why is isotopic notation important? Okay, so this question is fairly loaded, because to understand why isotopic notation is important, you have to understand what isotopes are. Okay, so you notice how when you look at the periodic table, right, you have very specific numbers when it comes to like the atomic mass units. There's a reason for that, actually. It's a combination of the percentages of their isotopes. So isotopes typically are, you know, found like they're more like whole numbers when it comes to atomic mass units, because that's how they actually wanted to base the weight of them. So like a proton is typically around 1 atomic mass unit, or, you know, 1 gram, technically speaking. But going like delving into that, we can actually take an example of carbon. Okay, so carbon, okay, is going to be 12.011. What you'd actually see in nature, right, it's not a carbon that weighs this arbitrary number, but you'd actually have this type of carbon. This right here is an isotopic notation. What it's saying is that its total atomic mass units, okay, is 12, and it has 6 protons. Well, that's usually what it means in terms of that. Based on the elements itself, you already kind of gave yourself the first part of the isotopic notation. Like the bottom, the subscript to the subscript, so not the superscript, but the subscript to the left is usually going to match what the element is. Another example, let's say we had oxygen, right? It'd be, well, actually, before we even write that, we just want to focus on the actual element number. So exactly, a better name would be the element number, okay? And as we remember, element numbers indicate how many protons they have. So now you're probably wondering what the above number is, the superscript, okay? That one is a total amount of protons and neutrons in that isotope. So, with that being said, if I said this oxygen has 8 neutrons, okay, then that would mean that the total here would be 16. Now, that's just an example of isotopes. What makes this important is, as you notice, you see here, right, it's 12.011. Not every carbon, okay, comes in like that. Okay, there are some carbons that are actually like this. Okay, carbon 13 is what they call it. So this one will be called carbon 12, and this is carbon 13. Okay, so interesting enough, right? Although they do bond fairly similar, their properties themselves are slightly different between carbon 13 and carbon 12. Carbon 13 has an extra neutron, which does changes a little bit of constituents and what it can do in nature. And it's also, I would say, more unstable than carbon 12, considering that there's a lot more carbon 12s in nature than carbon 13. So, in a sense, isotopic notation tells us what type of isotope we're dealing with, because when you think about it, right, these, I guess, molecules and stuff that are formed, they're not just formed from like these elements, like of these arbitrary numbers, although that's how we get molar mass. It's kind of like the average, in a sense, of all the different types of carbons, because they still form the same bonds. They're still overall relatively the same thing, because they have the same amount of protons, same amount of electrons, but in terms of what they're actually made, like the neutrons part in the nucleus, it does make it react slightly different in terms of ways that even I'm not fully comprehensive in. But the point being is that that's when you start getting to things like whether it's purity and stuff like that, as in there are many things whether it's the chirality in terms of like how it's structured, or even like what type of elements are bonded in it, that would affect molecules performance or how it functions. So in a sense, isotopic notation just helps us see what type of isotope we're dealing with. Okay, it gives us more information of how many neutrons there are. That's a key aspect. Okay, so for example, if we wanted to name this would just be oxygen 16, and I'm not sure what type of other oxygens there are, but so I don't want to list isotopes like that, but that in a sense is isotopic notation and why it's important. Okay, exactly. So let's see. Note that isotopes refer to all the variants of the same elements, while a nuclide refers to an individual species with specific atom number and mass number. Okay. So let's see. Isotopic notation. Yep. A is equal to the amount of element number plus the amount of neutrons it has. Okay. And they give an example of lead. You see the difference between the amount of protons and the total amount. There's exactly 125 neutrons. So that's pretty much what it's saying. How you break it down, you always want to subtract the subscript from the superscript to find out how many neutrons you have. Okay, exactly. And there's radioactivity, and elements that are more stable than others. For example, the reason why we have such a number close to 12 for carbon is because there's just more of these in nature, because they're just a little bit more stable than carbon 13. Okay, and you'll notice that as you get to bigger and bigger elements, that isotopes become quite crucial in explaining how you even get that atomic mass. Okay. So question 5.